All right. Good. Perfect. So I'm not gonna belabor the Steve fine point, but everyone do please go to this site visit 4:30 or 5 or 5:30 or 4:30 or 5, depending on who you are. This is Ray,
Hi.
undergrad
Yes.
here, going to tell us about imaging of lasers. Take it away.
Yes. Hello. So like Luke said, oh yeah, I get applause. Nice. So I'm going to be talking about how we see things smaller than light, which is a thing that you might not have needed to do before, but it's an important thing to be able to do. And I'll talk about why that is, and I'm also going to talk about how we do it, because it seems like it should be impossible. The other thing that we're going to talk about is how to take pictures with a laser, which sounds very weird, but I promise we will get into it. So to kick things off, I have a discussion question for you. So introduce yourself to your neighbor and think about the following question. So this is kind of a dumb question, it seems, but why aren't microscopes infinitely good, right? Like when I get a microscope, it can't see individual atoms. If it could, we would have known about them way earlier, and it would be way easier to do quantum physics. But we can't, right? Like microscopes can't see individual atoms, or at least not one that I can buy. So why is that the case? Like if these little diagrams about where the light goes are to be believed, we can just add more lenses or like make the lenses stronger or something, and then just see anything we want. We can zoom in infinitely far. But I mean, we can't do that. So for you to discuss, why can't we do that? Go.
You get back if you like. It's like I can hear you.
Ask Luke. I don't. That's not my computer.
Well, I'm just gonna see.
It's probably smart.
Yeah, my idea is that it's certainly like with other squiggly. And so like because of like the width of the squiggly thing, it's like if something has a width of less than it's really big, then there's probably some wacky stuff that happens there. That's not sort of
Well summarized.
Expert.
All right. I think we're done. Okay. So let's come back and does anyone have an idea that they'd like to share in relation to this question?
Mark does.
Okay. Hi, Mark.
Okay, so light is like a wave, right?
Yes.
And the wave has like a certain width.
Okay.
You know, it has non-zero amplitude, right? So there's probably something weird that happens when an object is smaller than the width of like the amplitude on the top to the amplitude on the bottom.
Okay. Anyone else have any ideas? No? Okay. So I'm actually not going to answer this right now. I'm going to answer it later because we don't have the right conceptual tools to be able to come up with a good answer for this. So I'm going to postpone optics for a bit, and I'm going to talk about how I got here. Because C prime made me. So at first, I'm going to start all the way back during my middle school experience, which seems like kind of a long way to go back, but it is important, I promise. So I went to a very weird middle school that did things very differently. The way that they encouraged learning is they got students to kind of pick a topic that they were interested in and then do projects in order to kind of explore that topic and explore it independently. And so that kind of gave me like the push that I needed, or I guess the motivation that I needed to kind of learn independently by doing my own projects. And the reason I learned that I was really interested in physics is because I did a bunch of projects and some of them were physics related. And I found out that I really liked working on the physics related stuff. So as an example of a physics related thing, me and a friend from the same school built a tiny particle accelerator in a shed because it was fun. And I learned a lot about electromagnetics and how to control charged particles and all sorts of things like that. But above that, I learned that, you know, physics is really cool and I want to keep doing this. So moving towards my high school experience, I went to high school. I was excited to learn about physics finally. And I got involved in robotics because of course I did. Unfortunately, the school that I went to kind of had a lot of problems. They didn't really have any advanced classes. they kind of struggled with class placement. The system was incredibly flexible. And because I had done a bunch of projects independently, I already had a lot of experience in the things that they were going to make me sit through a class in. And so during my high school time, I looked incredibly young for some reason. I didn't really have a clear gender identity, and I was also doing pretty well in the classes because I was pretty much just retaking them because they wouldn't let me skip. So they had me take like the very beginner classes. And it wasn't really a good combo. So I received a few targeted death threats, which was interesting. So I decided that, my safety personally and just a lack of complete academic boredom was more important than a high school diploma. So I unapologetically dropped out 2 years early, and I got a GED. So then I was kind of in this weird situation where I didn't have a high school diploma. I was 2 years younger than I should have been. I figured that few undergraduate institutions would actually accept kind of a weird student. So I applied and I was accepted to CU Denver, which is another campus than CU Boulder, but it's still CU. It's kind of complicated. But it was a more open-minded institution because it was smaller. It was more flexible. I also had spoken to professors there who could vouch for me a little bit. And so I did well in some classes at UC Denver, and so I was able to transfer to CU Boulder here without them checking my high school history. So I was able to get away with completely dropping out of high school and go to CU Boulder anyway. And then I ping-ponged back and forth between UC Denver and CU Boulder while deciding on whether to major in physics versus math. And so I finally decided on physics, and here I am. So I also took Phys 1400, which I think a lot of you know what that is. On my first semester at CU Boulder. And so I had a connection to one of the research groups, the Gopinath group. And so last summer, I asked them like, hey, are you looking for an undergrad? And they were like, sure, we can have you do undergrad stuff. And so I joined there in May with no optics experience, which was fun. So now, with that out of the way, let's go back to microscopes for a minute. So the first thing you should know about microscopes is that they're basically overgrown magnifying glasses. So you have a magnifying glass, people have been doing that for hundreds of years, and then they're like, well, I can't see anything smaller than, I don't know, a millimeter across or something. So they added more lenses and called it a microscope. And so here's a diagram of a microscope over here, but optically, we don't really care about anything except for these two bits, which is where the lenses and stuff actually are. And so we can kind of forget about the stand and everything. And from an abstract view, I know this sounds kind of weird, but a microscope should kind of look like nothing from your perspective looking into the microscope, but it should add additional magnification. So if I look at an object, I can see it, right? I can see it clearly. It's not as big as I'd like it to be if it's something small. I can't see clear details, but like it's not blurry. I can see it fine. So what a microscope should do, like, okay, so this is me staring at the remote. The sample's too small. I'd like to be able to see it bigger, but yet I can see it. So the idea is that I'm going to put something in the middle. I'm going to call that thing a microscope. And what the microscope should do is it should kind of make it look to my eyeball like the microscope isn't there and the sample is bigger, right? And so it should just look like I'm looking at a bigger sample with nothing in the middle. And so if you think about what that needs to mean, it means that the microscope is effectively going down, taking an image of the sample optically, and it's bringing it back up and it's showing it to me so that I can see the image. But it's adding some additional magnification in order to do that. And somehow magically it's doing everything optically. So this talk is about how we see things that are smaller than light, but it's worth taking a little bit of time to figure out how we see things that are bigger than light anyway. And a microscope is a great example of that. So there's another discussion question for you. If I have like a piece of photographic film, it's going to record the intensity of the light that hits it, as well as where that light hit. And let's say I have a painting on a wall, and I uncover this piece of photographic film, and I point it at the painting, right? If I take this plate of film and I go and develop it and look at the image that's on it, is that going to be a clear image of the painting? And if I go and put my eyeball where the film was and I open my eye, will I be able to see a clear image of the painting? Or like you could replace my eyeball with a phone camera and that would also work. Oh no. Yay, maybe. Yay, okay. Hope that wasn't happening the whole time. So the question is, if it's different, right? what do I do in order to turn one into the other? And if it's not different, if the plate of film and my eyeball give the exact same results, why is that, right? So I guess just compare the two systems and see what you can come up with. So go.
Like, I just. But like the idea that there's something good and something. Like, if I just pulled that up, so like, or if I just thought I pulled that up, it's something.
Okay, I think people are quieting down. So let's regroup. So does anyone have any ideas for the answer to this? Anyone? Okay. Fair enough. It is kind of difficult to think about. So that's why I have a demo for you that will hopefully make this a little bit easier to see. So light, from our perspective anyway, it kind of looks like it goes in straight lines. And we can use this to kind of, think about where light is going to go if we have some arrangement of components. Oh, please work. Okay, so here I have this is basically a very boring painting. So it's 3 stripes, and you can see each individual stripe is kind of just giving off light in all directions. And so, if you were to look at this, if you were to stand here, you can see my cursor and look at this, you'd see light coming from here, you'd see light coming from here, and you'd see light coming from here with a gap in the middle. So now let me grab that plate of film. Where is that? I'm going to represent that as a line. And so what's going to happen is if you look across this plate of film, you see that up here, there's some light. As you go down, there's more light, and then there starts to be less light again. But there isn't really an image of this painting on the film, right? Like we should see little gaps in the light, and there isn't a gap in the light. Hopefully everyone's convinced that if you just held up a plate of film to a painting, you wouldn't see an image of the painting. But hopefully you thought about, if you have a camera and you point it at the painting, you should be able to see an image of the painting because that's kind of the whole point of the camera. So what you can do in order to make a plate of film like this more into a camera is you can add a lens. And lenses, you've probably seen them before. They're in cameras, for instance. If I throw a lens here, what's going to happen, maybe, why is this not? Oh, my focal length. Okay, there we go. So you can see right here, the light is kind of going into the lens. The lens is doing some magic, and then the light comes out the other side. And you can see if I put the film here, this is exactly what we're looking for, right? Because there's some light up here, there's a gap in the light, and then there's more light, and then there's less light here, and then there's another gap. So if I have this plate of film with a lens in the middle, and then the painting, I've made a camera. I can see the painting on the plate of film. Yay. Okay, it's kind of a rudimentary camera, but it's still a camera. And you can also kind of see that this is the imaging system that we were talking about. Because if you go right here, right up against the painting, you kind of have the pattern that we want, right? You have some light and then a gap and then some more light and then a gap and then some more light as you move down. But as you move further away, that image kind of gets blurry. And then as you go on the other side of the lens, that image starts to unblur. and it appears again. So this lens is kind of taking an image from here and it's moving it over to this plane. And then the film is actually picking up the image that exists on that plane and it's turning it into an image for you, or it's turning it into an image that's on a piece of film. So that if you develop the film, you get a picture. And that is called a 2F imaging system because the distance between this painting and the piece of film should be twice the focal length of the lens. So let's talk about another type of imaging system, if I can pull it up, called a 4F imaging system. So the idea behind this is that we still have the same really boring painting that we're trying to look at. But if we take this lens away, this lens has a different focal length so that the image that it resolves is probably going to be way over there, and I don't want to go chase it down. So this lens is kind of like taking this image, it's turning it into not really an image, it's some blurry mess. And then we can put another lens, and when we throw the other lens in there, bam, we get another image again. And this is called a 4F imaging system because if the two lenses are the same focal length, the distance between this plane and this plane should be 4 times the focal length. So that's pretty cool, right? We can make different imaging systems using different arrays of lenses. And if you think about it, because you want your eyeball to be able to see the painting when you look at the painting, otherwise it's not a very useful eyeball. Your eye also has a lens in it, right? And so you're kind of taking an image that you're seeing and you're projecting it onto the retina, which is at the back of your eye, and that acts like a piece of film. And so your eye is like a camera in that regard. Okay, so now that we have that, we know about 4F imaging systems and 2F imaging systems, we can finally take a minute to look at a microscope. So the idea behind a microscope is to kind of can I zoom? No. It's unfortunate. There we go. So the idea with a microscope is to kind of combine a couple different imaging systems in order to get an image from one side to the other. And I know this is boring, but this will become important in just a minute. So you can see here, like we start with an image, right? It gets blurry, and then it passes through this fancy lens that we call the objective. And then right here, you can see it becomes the same image again. We have this bright band, and then a dark band, and then a bright band, and then a dark band, and then a bright band. And this image is about the same size as the original image, which makes it kind of a useless microscope because it doesn't actually magnify anything. So then what we do is we pass this through something called the ocular lens, which is, if I go back up to my microscope, it's this lens up here. So with the microscope, oh, by the way, the objective is this thing down here, that fancy lens, which is actually multiple lenses, but it kind of acts like one big lens. So it's going to form a 2F imaging system here because you have, your image and then you have a single lens and then another image. So then when that passes through the ocular lens, it kind of just becomes a blurry mess again. But what the ocular lens is doing is it's actually forming one part of a 4F imaging system, and your eyeball lens is forming the other half of that imaging system, because ultimately we want to take an image of the sample and project it onto your retina so that you can see what's going on. And so you can see that like after the ocular lens and the eyeball lens, then that completes the 4F imaging system. And then on your retina, there's going to be, this is not to scale, by the way, there's going to be an image of the tiny painting that you were looking at under a microscope. And so you can see how we can cascade imaging systems like this. As long as we can get an image from one point to another point, then we can just keep doing that. And so we can start to do imaging like that. So let's go back to the slideshow. We can start abstracting out and talking about entire imaging systems, which move an image from one plane to another, as you might have guessed. And sometimes these can do stuff like magnification or flipping the image, and that's what makes microscopes useful, not the flipping the image, but the magnification. And so in order to make a microscope, you take this 2F system, you put it together with a 4F imaging system, where one half of that is your eyeball, and there you go, you have a microscope. So that's all well and good, right? But there's another thing that you can do with this that actually ends up being more powerful. But for now, it's going to seem like a bit of a detour. And that's called laser scanning microscopy. And this goes back to the thing that I said at the beginning of the talk, which is that we're going to learn how to we're going to learn how to take images with a single pixel or with a laser. And so the idea behind laser scanning microscopy is that you can, when you have an imaging system that takes an image from one plane to another, you can always put an image into the output and get back an image on the input. And so the idea is that instead of using like an image on the output, we take a laser beam and we point it back into a microscope, basically. And then what you're going to do is you're going to take that beam and you're going to deflect it around so that it lands at different points on the sample that you're imaging. And hopefully your sample is flat. And so whenever your beam is on top of something that's bright and it's going to reflect a lot of light back at you, you're going to get a lot of light coming back from your laser. But whenever it's on top of something that isn't bright, you aren't going to get a lot of light coming back. And so the idea with laser scanning microscopy is that we can take a laser and we can scan it over the sample and look at the amount of light that's coming back. And then when we do that, we can, build an image with this. And so I have a little demo of this. Hopefully, that's not the right thing. I understand why that was not the right thing. There we go. So why is this here? Turn that off. These red strings or whatever, those represent some interesting sample that we're going to try to take an image of. And so as I run this microscope, you have this thing that is going to slowly sweep across the sample, and this represents the laser beam. And so the laser beam is going to kind of go through this grid pattern, and within this little circle right here, it's going to count the number of little dots that appear inside that circle. And so you can think about this as like, if you have a laser beam, each individual dot is going to scatter some light back at you. And so when you look at the amount of light that comes back, you're kind of taking a measurement of how many dots are inside that circle. And so as it does this, as it goes through scanning, what it's doing is it's going to like count how many dots are inside the circle. And it's going to reconstruct an image just by setting the point in that image where the laser was to be however much light the microscope got back. And so you can see that as I do this, you can kind of see it's like it's taking an image of the sample, although it's not a very good image. And if I turn down this, you can see it is an image of the sample, but it's all blurry. And so oh, that's not what it's supposed to be. That's also not, sorry. One thing that we can play with here is the size of the laser beam that we're shining on the sample. So if I reset this and I make the laser beam really big, where is that? Sorry, there we go. If I make the laser beam really big, then kind of the area of influence where you're going to see light coming back is going to be a pretty large area. And so when we scan this across the sample, there we go. What we're going to get is, first of all, we're going to get a lot more light because we're putting a lot more light on the sample with a bigger beam. But the other thing that you're going to see is when I turn this down, the image is way blurred, right? Because, it kind of has to be. When you put your beam somewhere in the middle, it's not just seeing one small area of the sample, it's seeing like a huge area around the beam. And so you're getting kind of this blurred effect as you scan your beam and reconstruct an image. So hopefully you can kind of see what's happening there. So the question that I'm going to ask you is if I want to get a very crisp, clear image, what should I try to do in terms of the size of this beam as it hits the sample? So discuss amongst yourselves. Okay, I think it's quieter. Anyone have any ideas? Yes, make it really skinny? Okay. Any disagreements? Okay, cool. So I'm gonna do just that. I'm gonna make it really skinny. So when I turn this way down, something like that, I'm gonna reset this. And when I turn the strength of the laser up, you can see that the beam is only like picking up the strands when it's very close to them. And so you get a very sharp image of your sample. And so this is kind of fun. So the question then is, how small can we get the beam, right? Because if the beam is an infinitely small point, you should be able to just scan over some tiny area and get infinite magnification, right? So the beam, to use slightly more precise terminology, I'm going to call this a point spread function, which means kind of like so for our circle, that was basically just a circle where, if a point is inside that circle, it gives you some light. If the point is not inside that circle, it doesn't give you any light. And so the point spread function, which is just basically the amount of light that you get back for a single point relative to where it is, in relation to the beam, that's called a point spread function. And so what you saw over here is that, I'm going to close these, sorry, go away. When the point spread function was really small, what we were seeing is that we aren't getting a very blurry image. And another way to interpret this is that everywhere we see a point in the sample, we kind of get a little miniature image of our point spread function. Like if you see this little solitary point over here, if we let this scan for another minute, that little solitary point gave us this little solitary point over here in our image. And if the point spread function was bigger, then we would have seen this little point appear in our image further away from where the point actually is. So everywhere there's a point in the sample, we're going to get a little miniature image of our beam over when we go to take an image. And so when this beam is bigger, you're kind of like blurring your image. When this beam is smaller, you're getting a sharper image. And this mathematical operation is called a convolution. We already did this discussion question, but I want to take a moment to point out that you can get all sorts of weird images by using weird point spread functions like this. So there we use circles or disks, but these are actually beads that we were imaging with the microscope that I'm going to talk about in a minute. These should be tiny little beads. They should just be points. But the point spread function in these images is very weird, right? Over on the left, it's kind of like this weird donut shape. Over on the right, it's like a bunch of concentric rings. And so everywhere there's a bead, I'm seeing a little miniature image of what the beam looks like when it hits the sample. So in the ray optics demo, when we think about just like rays of light going into the microscope and focusing down onto the sample, what we see is that they all intersect at this single infinitesimal point, which is great, right? Because if the beam is infinitely small when it hits the sample, we have infinite resolution. But we already know that we can't have infinite resolution because otherwise we could just like image single atoms and learn a whole bunch about the universe. So what's happening here? And the answer is that ray optics, where we had a bunch of light that converges at one point on the sample, that's just not accurate. The light doesn't all converge at one point. What happens in reality is that you kind of get this small beam on your sample, and it doesn't become infinitely small, which means that we don't get infinite resolution, unfortunately. So, as Mark was saying at the beginning, we can resolve this discrepancy if we think about how light wiggles, right? Because the reality is light doesn't travel in perfectly straight lines. When you zoom in, it starts to become this wavy phenomenon that seems to travel in straight lines when you zoom way out. But in reality, it's kind of this oscillation of the electric and magnetic fields that are kind of pouring energy into each other. And because one can be derived from the other using Maxwell's equations, we just think about what the electric field is doing, and then we can describe the magnetic field later if we want to, but usually we don't want to. So first of all, I want to clear up a misconception, which I think a lot of people had because I had it. And so if light is a wave, right, if it's squiggling up and down, the question is, can I bend it through obstacles, right? Can I have it wave up and down? These black boxes are supposed to just be like a solid thing. Can I do this, right? Does light actually physically go up and down? Does anyone have an answer for me? Okay, fine. We'll make it a discussion question. Discuss amongst yourselves.
I say, in the next match, these was in part of the brand.
Okay, it's suddenly very quiet. Does anyone have an answer? Please. Yes.
Really small, so
Okay.
it's like you wouldn't be able to just spend it like an object. Maybe if it was like super small.
Okay. So you're right in that, you know, if we actually tried to draw it like a wave like this, it would probably be really tiny. But the answer is actually that this is a bit of an incomplete picture. When people talk about the wave nature of light, they like to draw these cartoonish diagrams like I did just a second ago, where it like squiggles up and down. But that doesn't mean that light literally goes in a wave. In fact, I mean, it is a wave, but it doesn't literally go up and down. And so what you can think about then is like light is kind of, or the electric field anyway, which is one of the things that's doing this waving, is like a bunch of arrows that are anchored everywhere in space. And so really what happens is that the light travels along a single line. It doesn't literally swerve up and down. But what's happening when we draw those waves, what we mean is that every little arrow along that line is pointing up and then pointing down and pointing up and then pointing down. And so if you were to trace out all the tips of those arrows, you'd see a wave. But yet all the arrows themselves are actually all like anchored to and are a property of the space along a thin little line. And so light literally does not squiggle up and down. It follows a line, and then if you trace out the electric field, you end up getting something that looks like a squiggle. So the answer is that it doesn't pass through unaffected, because it doesn't squiggle up and down like this. So now that we talk about imaging systems, we have this idea of imaging systems where they take some pattern of rays moving through some plane, and they move that pattern from one plane to another. So if we want to update our conception of imaging systems to think about how this would work when you're thinking about light as a wave, we could conjecture that an imaging system, what it does is it takes some pattern of the electric field moving up and down, and it moves it from one plane to another. So it kind of like records the plane somewhere and then plays it back on a different plane. And it uses some optical magic in order to make that happen, but that's still what it's doing. And when you think about this, a consequence that comes up is that, okay, you have this imaging system, it's like a microscope or a magnifying glass or whatever, and you have some plane on one side, and there's some wiggling motion in that plane. We don't really care about what the actual wiggling is. But that wiggling is going to correspond to some light. And that light is going to pass through the imaging system. And ultimately, the imaging system is going to use some light to reconstruct the same wiggling on another plane. And that means that whatever wiggling motion existed in that first plane kind of determines the way that light needs to move through the imaging system. And so if you were to think about the entirety of the universe as kind of a bad imaging system, it means that if you pick some arbitrary plane and you look at how the field is wiggling on that plane, you should be able to figure out the plane or the electric field everywhere else in the universe, which is a bit abstract, but we'll talk about some examples. So this is a bit of a useful tangent, which is called holography, which really just is the discipline of making holograms, because holograms are cool. And when I say hologram, I think a lot of people will think of like, you know, the Back to the Future hologram where there's like this giant 3D thing. And I think that would technically fall under the definition of a hologram. But when I'm talking about a hologram, I'm talking about something like this. So we'll watch the video and then we'll talk about it. So there's this plate here, some magical plate, and you can see an orange behind the plate, but yet the orange isn't actually there, right? The plate is creating this illusion of something being behind it, even though there isn't anything behind it. And what's going on there, it's actually slightly easier to see this when we step down into one dimension. And for that, I have another, it's not what I wanted. I have another demo for you. So we're going to make a one-dimensional hologram. So if I have this infinite string that's just sitting, and a string is kind of a one-dimensional thing. So I'm going to poke this string in the middle. And what's going to happen is that I'm going to get a pulse that goes to the right and a pulse that goes to the left. And this is actually what would happen. If you took a string and you poked it, you would get this kind of like wavy behavior. And you also see that when you throw a rock into a pond, you get these pulses that travel outwards. And so I put a point here that's kind of going to ride along this pulse as it passes through. And this point is going to kind of sit there and think, okay, what am I doing? And so the pulse is going to go up, and then it's going to go down, and then it's kind of going to go back to where it was as the wave passes through. So what I claim is that by looking at the motion of this point, you should be able to figure out everything that the rest of the string is doing, at least in one direction. And so what I'm going to do is I'm going to take another string, right, another infinite string, and I'm going to put a similar point on it, and I'm going to mechanically connect the first point to the second point, so that when the first point moves, the second point moves as well. And what's going to happen is that as I hit play, as the pulse moves through the first point, it's going to pull on the second string, and you're going to end up with another pulse that goes off to the right that looks like the exact same pulse that traveled through the point to begin with. And so this is cool, right? If we look at the motion of a single point, and we know that what we're looking at is the motion of a single point that's on a string, we can reconstruct the motion of that string everywhere to the right of this point that we were looking at. And this is basically a one-dimensional hologram. So if we look at what light would look like, it would look like a wave that's moving to one direction, right? You have this wave that's kind of passing. And so if you're looking at the motion of a single point, which in 3 dimensions corresponds to looking at how light is passing through a single plane, what you should be able to do is then grab another string, right, and kind of play back the motion of this point. And what's going to happen is that we're going to get another copy of the wave that goes in the same direction, which is to the right. And so this is interesting, right? We're playing back the motion of a single point, and that actually gave us the motion of the whole string in a specific direction. And so what this hologram is doing, it's pretty much the same trick. It's recording the wiggling of the fields from when there was an orange there, but just along a single plane. And then it's going to play back that same wiggling action. And the result is going to be the fields that originated from light reflecting off of the orange. And so as you move your head around and everything, you're going to be passing through those fields, and you're going to be able to see what you think is an orange, even though it's just the field that's being played back along a single plane that is the hologram. And it's kind of mind-bending to think about. But this ends up being important when we think about imaging systems. So now that we've seen that happening in one dimension, we're going to talk about this happening in 3 dimensions a bit more. So I will open this demo for you. So what I'm going to do is I'm going to press play, and this is a single plane, and I'm drawing the electric field as these dots that move up and down. So if the dot moves up, that means the electric field in that location is pointing upwards. If the dot moves down, that means the electric field is pointing downwards. And so we're seeing this oscillation along a single plane that's moving up and down. And that's kind of interesting. And so what we're going to ask ourselves is like, look, we have the wiggling action on a single plane. And we just showed that if you know the wiggling action on a single plane, you should be able to figure out the wiggling action in the rest of space. And so the question is, what is the wiggling action in the rest of space? And the answer is it looks something like this, right? And the way that you can think about this is you have light that's kind of moving along the x direction. And if it's moving in that direction and you're kind of looking at a slice of it, you're seeing the electric field in that slice going up and down and up and down. And that reconstructs the wiggling action that we were seeing on that single plane. And so just by looking at that single plane, and if we know the light isn't moving backwards, then you can say with certainty that what you are looking at is light that is traveling kind of perpendicular to the plane. And you're seeing this wiggling action. So then what I'm going to do, oh, and also make a note of the wavelength of this light, which is kind of the distance between peaks. I'm also going to draw this for you, which kind of just shows you what the wiggling is, but it's on a plane, so it should be easier to visualize. I'm also going to turn this on. You'll see why I did that in a second. So this seems all well and good. So then what I'm going to do is I'm going to add some like wobble across the plane, and we're going to see what this corresponds to. So I'm going to turn up this thing, which I've called K1 here. You might hear me refer to it as the tangential wave vector, and that's because that's what that is. So as I turn this up, there's kind of, I'm going to introduce some wiggling that's happening along the plane. And when I turn this all the way up to 1, there's some wiggling that's happening along the plane. And the wavelength of this wiggling, if you look at like the distance between peaks, is the same as the wavelength of the light that was traveling. And so the question is, okay, I know the wiggling on a plane. What does the wiggling look like in the rest of space? And I'm going to reveal the answer. It's kind of underwhelming. The light is actually just moving in the y direction. So you could probably have guessed this. You know, we saw the wiggling moving in that direction on the plane, and we have the light moving in that direction when we turn on the fields in the rest of the universe. So we have a couple things. So we know that when the tangential wave vector is 0, so all the points are just wiggling up and down in unison, that corresponds to light that's kind of passing through the plane. And when the wavelength of those oscillations along the plane correspond to the wavelength of the light that we know is traveling, we know that that corresponds to light traveling along the plane, kind of sideways. And so the question is, what happens in between these? So if I go over to this demo, what would... So, okay, we have this sort of motion, not that. We have this motion. We know that means light is moving sideways. We have this motion. We know that means light is kind of moving towards you. What about somewhere in the middle where the plane isn't, like there isn't much oscillation along the plane, but there's a little bit. So that is a discussion question for you. Discuss.
Oh. Maybe
Okay, we're running short on time, so I'm going to cut this one short. Anyone have any suggestions? I heard good things coming from this group.
We said that like probably
Somewhere in the middle, right? Okay. And let's go here and we'll see what it actually is. So if I have this sort of wiggling, and I turn on this, you can see that the only solution to this is kind of a wave which is moving not quite perpendicular through the plane, not quite across it, but kind of at a weird angle relative to the plane. And you can see that this corresponds to the wiggling action that we were looking at earlier. And so when you turn up this wiggling along the plane, what you're turning up is kind of the angle along the plane. And you can see this as I start to turn this up. So if I pause time for a minute, turn this off, start time again. I start from here, I go all the way up. There we go. This is kind of what this looks like on the plane. So then I'm going to turn on the fields in the rest of the universe. And I'm going to show you that as I turn this up, what's going to happen is that the light kind of changes its direction such that at the end, it's going straight along the plane. And so by varying the amount of wiggle that I'm putting like this, I can vary the direction that the light that this wiggling action corresponds to is traveling in. And you can kind of see that happening like this. So the next question is about what happens if this tangential wave vector thingy exceeds this number. So 0 corresponds to this. 1 corresponds to the maximum amount of wiggle across the plane that we've seen so far. And it also corresponds to light traveling straight along the plane. What happens if I increase it to be something like this, right? What sort of action does that correspond to? If you were to see these fields on a plane, what would you think that means about the light that's passing through it? And I'm not going to make this a discussion question because I don't think we have time. But the answer is actually something very weird and something that you might not expect, but it really does happen. And so we saw that when there isn't any wiggling across the plane, we have light moving through it. When we turn this up, it starts to move perpendicular. And then what happens is if we keep going, we're going to get this thing that doesn't quite look like a wave. And so it's going to start off next to the plane. It's going to be wiggling. And then as you go further and further out, the wiggle is just going to kind of decay. And so this light, it really isn't moving anywhere, right? It's just kind of there and it's wiggling up and down, but it's not really leaving the plane. And this is what is called an evanescent wave, which is kind of a wave that isn't really waving, like it's waving in one direction, but as you go further away, it just kind of dies out. And this only happens in situations like this. These evanescent waves exist. They're kind of interesting. And so let's go back to our laser scanning microscopy, right? The idea is that we're going to try to create some beam on a sample. And if this is a large beam that's on the sample, so when it hits, its diameter is way bigger than the wavelength of the light that you're dealing with, which is kind of like the period of wiggling of the light itself, then no one really cares, right? Because this beam doesn't have sharp detail. And if you wanted sharp detail, you'd have to have some components of the wiggling on your sample plane that are kind of wiggling with high frequency across the plane that you're talking about. And so because there isn't really any sharp detail, no one cares, and evanescent waves don't really start to show up. But when we're going to talk about a small beam that we're trying to cast on a sample, what's ultimately happening is we're taking a laser, we're passing it through some magical device, and then we're going to be sending out some light, which will try to converge on the single small beam on the sample. And there are sharp edges in this beam that are much sharper than a single wavelength of the light. And so when that happens, in order to reconstruct that spot on the sample, we need some components of the beam that hit that plane to be oscillating across the plane with high spatial frequency. And we saw that that can't really happen, right? Once we exceed the like normal spatial frequency of the light, the waves don't really propagate anymore. You can't really get them to go in a particular direction. They kind of just don't really go anywhere. And so these higher spatial frequencies that make up the beam as it hits the sample, they have to come from this lens array and they have to make it to the sample. But because that distance is much longer than the wavelength of light, any evanescent waves will fully decay by the time they get to reach the sample. And so what happens in this case is that these higher frequency components of the beam hitting the sample are effectively cut out. And so we're taking an otherwise normal beam and we're removing the sharp edges from it. And what happens is unfortunate. The beam actually gets bigger and it becomes this thing called an airy disk or an airy pattern. And the problem is that with this kind of cutoff, the size of the airy disk that you'll get when you remove these high frequency components from a small spot the size of the disk that you'll get is completely determined by the frequency of this cutoff. And we know that the frequency of this cutoff is determined by the wavelength of the light that we're working with. And so when we try to make this beam smaller, it just means that we're adding higher frequencies to it in order to make it smaller. But then those higher frequencies end up getting chopped out because they become evanescent. So we're stuck, right? We can't make this beam any smaller because it would require higher spatial frequencies on the sample, but those can't propagate to reach the sample. So no matter how small we try to make the beam, we get this airy disk that's the same stupid size. And we call that being diffraction limited because the fundamental wave-like nature of light is stopping us from making a smaller beam on the sample. And the other way you can think about this is, and if any of you are like quantum mechanics fans, is with the Heisenberg uncertainty principle, which says that you can't know the position and the momentum of a particle of light at the same time very accurately. And so when you have this tiny beam, it means that you know the position of the light very accurately because it's in this beam and this beam is small on the order of the wavelength of the light that you're dealing with. And so what will happen is that its uncertainty and momentum laterally becomes huge and the beam will try to make itself expand again. And so that's what happens when you hit this equilibrium where the beam can't get any smaller, you have an airy disk. And you can kind of look at it both ways. It doesn't really matter. And so, okay, we have this beam. It's as small as we can get it, which means that our image is going to be fundamentally blurry. But what if there's a thing that we want to see that's smaller than this airy disk that we can make, which means it's much smaller than the wavelength of light that we're using? Well, you could think, okay, this limit is proportional to the wavelength of the light. So let's use light that has a shorter wavelength, right? Like X-rays. The problem is that it's going to be way more energetic. And if you're trying to image something that's alive, it's not going to be alive for very much longer if you start throwing really high energy X-rays at it. And it's just like, that's not really going to help. And people do X-ray microscopy, but they usually involve destroying whatever they're looking at because they're bombarding it with very high energy photons. And so you might think, okay, well, maybe light is just cursed. So let's use something like electrons that hopefully won't have the same behavior. And well, the problem is electrons are actually waves because like someone from quantum mechanics said so. And so we still have this limit. The thing is electrons are much heavier. So the wavelength that they have is really tiny. It's like a few picometers compared to the few hundred nanometers of light. So light is like hundreds of thousands of times bigger. The problem is that electrons are still really energetic. So if you're trying to throw these at some sort of delicate living sample, it's really not going to survive that. Also, electrons like to be conducted through metals. And this is a thing that people do. It's called electron microscopy. But they usually have to make their sample metallic first by spraying it with metal ions. And again, if you have something alive, it is not going to survive that. And so this seems like an impossible problem, right? We can only really use light and we can only really use low-ish energy light, like the light that we see. But yet we have this fundamental limit where we try to focus it and it just says no, and it won't focus anymore. So in order to do this, we're going to take a little bit of a detour and we're going to think about what laser beams look like. And so we're used to a laser beam that kind of looks like this, where, you know, it's bright in the middle. It's not so bright on the edges. And this is actually a solution to the equations that govern how light works. This is called a Gaussian beam because if you look across it, it looks like a bell curve. And this seems unrelated, but bear with me. If you have a string that's vibrating on like a guitar or something and you pluck it, you're going to see an oscillation pattern that kind of looks like this. And that's what we're used to seeing. And that's a solution to the equations that govern how the string has to move. But if you pluck a string in the right way, you can get all these weird modes that show up. And this actually contributes to what instruments sound like, which is fun. But these different modes of oscillation show up. And they're both kind of similar situations, although admittedly strings are in one dimension and light is in 3 dimensions. So the question is, does this apply to light, right? Can we come up with other modes, other fundamental ways of oscillating that the electric and magnetic fields can technically do? And the answer is, you bet, right? There are all sorts of these weird exotic spatial modes that exist out there that we're not really used to seeing because they're kind of hard to create. So the ones on the left are called Hermite Gaussian modes, and they will be our friends in a minute. And the ones over here are called Laguerre Gaussian modes, and they will also be our friends in a minute. And these modes are really weird, like we're not used to seeing them, but we can visualize them in Desmos, and they get weird. So remember we had a plane that was wiggling. When we start playing this. This is a normal laser beam. So you can see there's like more wiggling in the middle. And then as you go towards the edges, it gets less wiggly. And if we turn on all of space here, it gets kind of complicated. We have this tube of light that's wiggling, but it's mostly in the middle where the actual wiggling is happening. And this is a laser beam. This is the normal laser beam that you get out of a little handheld laser pointer. The thing is, weird other modes exist. Like this mode exists. This is fun. This is a Hermite Gaussian mode. So it's wiggly, but you can see the wiggling is mostly concentrated on the edges, and there isn't really any wiggling in the middle. And these can actually get kind of crazy. Like you can have this one or this one. And they kind of come in these like grid patterns. And if I turn on all of space for this, it's a mess. But you can kind of see there are like these tubes where most of the light is concentrated. Or most of the wiggling action is concentrated. And you can see that this corresponds to like the intensity patterns that we were just looking at a minute ago. So another piece of the puzzle that we're going to need is something called fluorescence, which is something that certain molecules can have that you're probably used to if you've played with like glow in the dark stuff. The idea is that we can get a molecule and we can throw some light at it. And what that light is going to do is it's going to take some electron somewhere and it's going to bump it up to a higher energy level. And then the molecule as a whole has some energy. The amount of energy that the molecule has decreases a little bit through some weird quantum mechanism. And then the rest of the energy is emitted as another piece of light called a photon. And so first of all, you can put fluorophores, which are just fluorescent molecules, in whatever you want, right? So if you have a sample of tissue, you can throw some fluorescent molecules in there, and the tissue won't mind too much. So it's not too limiting. If we want to specialize to just looking at things that are fluorescent, that's okay. The other thing that we can do with fluorophores or fluorescent molecules that's interesting is we can do something called stimulated emission, where we take, so here we're putting in blue light. You do that. We're putting in some blue light. A little bit of that energy is being lost, and then we're giving out some green light. And so the idea is that if we shine green light on the fluorescent molecule, we can force this transition to happen whenever we want it to. Through, again, some like weird quantum magic or something. So what this means is that because the fluorescent molecule is going to have some spectrum, some range of energies of light particles that it can emit, if we bombard this fluorescent molecule with some wavelength that is right on the edge of the different energies of light that it can give out, what we'll do is we'll constantly trigger this transition to happen, but at whatever energy of light that we're shining at it. So in our case, we use a fluorescent molecule that gives off some green, some yellow, some orange, and we bombard it with orange light. And when that happens, all the fluorescent molecules that get excited, normally what would happen is they would decay and then mostly emit green light, but a few of them would emit yellow light. But instead what's happening is because they're being bombarded with so much orange, all of them, when they get excited, instead of decaying back to what's called the ground state, which is just zero energy normally, they'll instead be forced to give off a photon that is orange. And we can use this to our advantage. And we can actually use this to exert more control over what our point spread function looks like. It's kind of like as if each little fluorescent molecule was like a little, I don't know, computer or something that you could control individually. So you could tell them, hey, you light up, you don't light up. And you could image something that way. So here's an idea, right? We have these higher order spatial modes. One of them looked like a donut, and we literally call it a donut. So what's cool about these spatial modes is that when you focus them, you can actually have some features get smaller than this fundamental diffraction limit, because of just how that's how it works. So if you take a spot of some blue light or something, and you don't do anything, right? You're going to have these fluorescent molecules. They're going to light up. They're going to emit some green light. And there's going to be this region of fluorophores that are going to be activated, and they're going to be giving you green light. And this corresponds to our point spread function that we saw earlier, because we had a beam like this, and then all the fluorescent molecules within the little circle got excited, and then we picked up that much light. But if we take this same spot, which again is diffraction limited, so we can't make it any smaller, and then we take an orange donut, or one of the Laguerre-Gaussian modes, which is donut shaped, and we also focus that on top of the spot, what we can make happen is, because this orange light is going to be causing all these fluorophores to not be able to emit green light properly, it's going to be kind of like disabling them wherever the orange light is hitting. And so the only fluorescence that we're going to get is wherever that excitation beam originally hit and where the orange light wasn't hitting. And so because the orange light only doesn't hit at like this small little hole in the middle of the donut, the only fluorescence that we get corresponds to this tiny hole, which is much smaller than the original excitation beam, which was this. And so back in our Desmos demo, what we can do is we can have a large beam, right? This corresponds to being diffraction limited. We can't make this beam any smaller. And then what we can do is we can turn up this depletion, which is donut shaped. And so you can see that like near the middle of the beam, it's not really going to deplete anything, but then towards the edges, you're going to have a lot of orange light. And so if you take this normal curve, this normal point spread function that we're used to seeing, and you turn up the depletion, everywhere the depletion hits, it's going to kind of silence the fluorophores. And so the effective point spread function that you get is actually just going to be this tiny spike in the middle. And so if we were to image with this, we would get a much crisper image because we're getting more localized fluorescence wherever we decide to put our beam. So this actually works. You can image stuff with this. You can image super resolution. That's pretty cool. Here's an image that you might have seen where you use this process. And so here are some beads, which are supposed to be way smaller than they appear here. But because you're exciting with this giant beam by comparison, you are not really seeing the true size of the beads. But then you turn on this STED lasers. STED stands for stimulated emission depletion, which describes the process by which we depleted the fluorophores. And bam, you get tighter resolutions. And so what's happening here that's really cool is we are seeing things that are smaller than the diffraction limit. We had this fundamental limit of the spot that we could make, and we have just blown past it using this technique. And so a problem that you run into is like, STED is hard, right? It takes up a whole table. This is a picture of our actual table. You can see the orange light is the light that we actually use to make the donut. But if you want to make this smaller because you wanted to image like a live animal, you can't really mount an entire optical table to an animal in order to image it. I mean, you could, but it would probably make the animal angry. So instead, we need to try to miniaturize this. And so we might think about using what are called optical fibers, which are just these like small rods of glass, basically surrounded in other glass. And it's worth taking a minute to think about how weird glass is, because glass is transparent, right? If you shine in some light, you're going to get the same amount of light out. But it's not invisible, right? If I hold up a chunk of glass, you can see that the glass is there, even though all the light that goes in comes out. And so the reason that that's happening is because of something called refraction, where you have light waves that actually slow down inside the material, and this causes light to bend. And so you get this sort of effect. And so in a rod made out of glass, you have light traveling along the inside, and because it's slower, the distance between the peaks of the wave will kind of be scrunched up. And so inside the fiber, the wavelength is actually smaller. But what's happening is that the fields on the boundary of the piece of glass have to match, because you can't just have like an electric field inside and then it suddenly vanishes right at the outside. So what the outside space sees outside the fiber is a bunch of wiggling along the edge of the fiber. And that the period of that wiggling is shorter than the wavelength that light normally would be on the outside. And so we saw what happens in that case. We saw that we got evanescent waves, and they don't really propagate. And so what happens is, in an optical fiber, you have these waves that kind of exist at the boundary, but they can't really leave. They're stuck in the fiber. And so you can send light down a fiber, and this is how the internet works. The problem is that when we try to send a donut mode into a fiber, the fiber actually doesn't like it. It's not really a mode of the fiber, because fibers, in addition to just carrying light, they also have specific spatial modes that they can support. And so when you try to send a donut mode in, it kind of gets split into two different modes that evolve independently and then interfere on the other side. And if you like bend the fiber a little bit, this interference pattern will change and you won't get proper imaging because what you get out the other side is not a perfect donut. It's some like weird amalgamation. So what we do in order to make our donuts come out of the fiber is we take two modes that you've already seen. There's this one and there's this one. And we add them together, but we don't add them together in the traditional sense. We add them together in the same way that if you turn on two flashlights and both point them at the wall, you're adding together the light of the two flashlights. Because the two flashlights are not really in sync with each other, right? The light that is being emitted from each flashlight, it's not all wiggling in exact sync. And so what happens is on average, sometimes when it hits the wall, it cancels out. Sometimes it doesn't cancel out. And so the average effect is that just you're adding the light together. And so when you do this, when you add these two modes together, but you do it what's called incoherently. So you take two different sources that don't have a consistent relationship in whether they're in sync with each other or out of sync with each other. You add these together, you get something that looks like a donut, but technically isn't. And because each one of these modes is actually like a real mode in the fiber, they will both behave independently, but when they get merged back together on the other side, you don't get this interference. And so now that we have this, we can actually make a whole setup, which is that table that I showed you earlier. So we take our excitation beam, which is technically infrared for other reasons. You can ask me about it if you want. And we send that into a fiber, which is just gonna like, carry it from one side to the other. And that's gonna create our nice little diffraction limited spot when it hits the sample. The other thing that we're going to do is we're going to take an orange laser and we're going to put it through this thing called a spatial light modulator, which is going to create a single one of these. And then we split it into two halves. One half goes through an optic called a dove prism, which will rotate it 90 degrees. And what's important is that the difference in path length between the two paths that the laser can take is long enough that by the time they're merged back together, the laser is not in consistent sync with itself in some ways. So when they're merged back together, they're being added incoherently, which means they can't interfere with each other. And then we jam them into a fiber, and they'll both evolve independently in the fiber, but it doesn't matter because they're added incoherently. And then we just send all of that right into the objective, which is literally straight from a normal microscope. And that's going to focus all of that down really tightly. And so we get a donut on the sample, and we also get our little excitation spot on the sample. And so with those two things, we can surpass the diffraction limit. Unfortunately, we do have to scan that beam around, which is not fast. So it takes like 10 seconds to capture a full image because you have to scan the beam back and forth. You can't just like look at the whole thing at once. So, it doesn't have great FPS, but it works. So why bother? And we touched on this a little bit. But like you could not use electron or X-ray microscopy, which can surpass this diffraction limit, but you just can't use them to image something living because it won't be living anymore by the time you've imaged it. And so there are things that are living that we want to be able to image. So like a mouse brain, right? As the mouse is alive, we want to be able to image its brain. And you could not do that with an electron microscope. The other thing that we want to look at is what are called dendrites, which appear in neurons, which are the cells that make up your brain. We're used to thinking about like, a cell, but then they have this giant tree of basically wires, but they're more complicated than wires. They do important information processing. But the problem is these wires are too small to see with a normal microscope. They're like a few tens of nanometers across. So you can't see them, and they have all this fine structure that you just can't really see unless you go to an electron microscope. But we can see them because we can see tighter than the diffraction limit. And we can actually see them while they're living, which is cool. So now that that's out of the way, I want to talk to you a little bit about like what a day in my life looks like. And I promise this will be fast because I think we're out of time. But you can I threw up some images over on the right if you want to look at them. They're just random things that I took pictures of because I thought they looked cool. So I'm doing the normal undergraduate thing, right? I'm attending classes. I'm also LAing for Phys 1400. I do that sometimes. But if I'm not doing that, I'm usually in the lab if I'm on campus, and I'm probably aligning something because the reality is this whole setup, all the beams are just totally pesky. They need to be pointed in exactly the right direction, and tiny little drifts because air currents or whatever will get them to point in slightly different directions, and you need to make them all point in the right directions again. So the most annoying part is trying to get these two modes actually into the fiber, because if they're off by like a few nanometers, the fiber just says no, and you can't actually push the light into the fiber. So it's kind of annoying. I'm also, if I'm not doing that, I'm probably hunting some weird issue with the microscope, because the microscope that we have is cursed. It just random things will go wrong. It's not great. I'm also probably analyzing lots of images of beads, because we've taken images of beads, which I know is kind of boring, but we need to be able to characterize exactly how good our resolution enhancement is because of this whole STED thing. And so I'm probably analyzing some images of beads, or maybe I'm writing some code to analyze some images of beads. Not exactly very exciting. Also, trying to get STED imaging happening in a sample is just, it's really finicky. So often I'm just trying to actually get the microscope to behave. And the ultimate goal of all of this, which I've only really been able to do for like 20 minutes over the past several months, is collecting a bunch of STED images at various depths in various samples. Because one of the things that we're trying to characterize is how far into a sample can you measure before everything gets messed up. So you just kind of make all the beams focus further in, and then you should be able to image at depth, but that doesn't always work. So we're trying to figure out how well that works at various depths. And so even though what we're doing is kind of conceptually cool, I don't really interact with it that much. I'm mostly just twiddling knobs very precisely in order to try to get the stupid fiber to carry the modes that we want. So I guess a day in my life as a research undergrad is not particularly exciting, but it is still fun to be able to mess with the equipment that we have and to try to get the stupid microscope to work. So I'm sorry I went over time, but that's the end. Does anyone have any questions?
Thanks, Ray. I know we started a little late, so if anyone has to get out of something else, feel free to do that, but otherwise, floor's open for questions.
Yes.
So, you know, you mentioned go better with diffraction, but how much better with diffraction? An order of magnitude, a factor of two, what is?
Yeah, so I forgot to mention this. The diffraction limited resolution, so like the average radius of the point spread function that we normally have is on the order of a few hundred nanometers. But if you do STED properly, you can get down to about 50 nanometers effective point spread function radius, actually diameter. So it is a pretty significant enhancement. But it's not quite an order of magnitude, unfortunately.
And do you know if there are people who got ways to try to be instead?
Yeah, so the STED is kind of, as far as I'm aware, the best super resolution, which means you're surpassing the diffraction limit technique that really exists using nothing but light. I mean, people use electron microscopy all the time, but it's not exactly the same. So yeah, I don't think there's another technique that gets you tighter than that, fortunately. The mode that we use, the donut mode, already has the smallest hole in the middle of any spatial mode that exists, and we can prove that that's the fact. And we can't focus it any tighter than we already do. So we kind of have hit a fundamental limit for STED in much the same way that we've hit a fundamental limit for normal microscopes. So 50 nanometers resolution is probably about as good as STED is ever going to get.
Oh. Like across.
Yep.
You take pictures of like atoms and stuff.
I don't think so, no. You can't get that tight, but you can get pretty small. I'm not sure, actually. I don't know much about electron microscopy. Yep.
What kind of microscope are you set up? Just like
Yeah, so it's kind of this horrible Frankenstein abomination that I don't really have a picture of. But we've kind of have the guts of a microscope, like on this big stage where we send beams into the bottom of it. It's actually upside down. It's what's called an inverted microscope. So we have the objective pointing upwards, and then we put the sample on top of it. And then we send beams into the bottom of the objective and collect what comes out. So all in all, it probably takes up about the size of a small room. It's not small. But the importance of the fiber coupling bit is that you can have a whole room to generate the modes that you need, and then just like plug a fiber into that. And then on the other end of the fiber, have all the nice light that you want. And then just have a little device that you connect that to. And then you effectively have a miniature microscope that you can put on a mouse or whatever. So yeah, it is kind of horrific in its current stage, but it can be miniaturized.
Do you think this is as good as microscopic imaging?
I mean, it depends on how you define a microscope, right? Because an electron microscope, where you're sending electrons at your sample, is going to be able to image way smaller things than this. But it's also really destructive. So in terms of like just using normal light, I think this is probably about as good as it gets. Unfortunately, I wish we could use normal light and see normal atoms, but I don't think we can.
Could you use other elementary particles other than photons and electrons?
I don't think anyone's done that. In principle, yes, but anything that I can think of, unless you're trying to use like neutrinos or something, would be more energetic than an electron and probably just harder to deal with. That's a good question, though. I don't know if anyone's tried imaging with some weird particle. So that's true. Yeah, not exactly very high resolution imaging, but
They actually do neutrino
really.
with solar neutrinos.
Hmm.
Like the X-ray neutrino
Yeah.
radiation, Fukushima, where they
Oh.
kind of plan how that on mess up that place.
That's cool. They probably can't see tiny features though,
Oh, no.
because
yeah,
it would be hard to
absolutely
put them in a lens and focus them
Yeah.
down. So
All different, light modes have like a fundamental limit.
have a fundamental limit, you said?
Yeah, it's like, just the Gaussian has X models right there. We all have.
Yeah, they do. So yeah, you're exactly right. Each mode, there's a complicated way to calculate this, but there is kind of a fundamental limit that you can focus each mode to before you just can't do it anymore, or before you end up destroying its contents. Because like you can't fit a whole mode into something that's much smaller than a wavelength. Because light itself just can't really carry that information at some point when you get small enough. So yeah, the other way that you could calculate this now that I'm thinking about it is that each one of those modes, you can kind of think of it as an infinite sum of a bunch of plane waves, which are, they're kind of waves in a plane, like I was showing with the wiggly on the plane demo earlier. And so I think you could think about the spatial frequencies that you need in order to reconstruct a mode at some specific size. And then just realize that you can't get too high, otherwise those will be cut out. Sorry, I don't know if that answered your question, but yeah, there is a limit for each one.
More questions? Let's thank Ray again.
Sorry, I went over time.
Back next semester. Good luck on finals. Enjoy this.
Yeah, it's for students, remember to check your, the announcements, remember to sign in again for the.